Let's take a look at some solutions for assignment 4.3. Our first example here, after you watch the two video problems, our first problem doesn't fit either of those exactly, so let's watch carefully as we make a diagram here. So we've got a plane flying at a constant speed over a radar station, and when it's over the radar station, it is at an altitude of 1 kilometer. So let's put the radar station here, and the plane at some point in time is 1 kilometer above the radar station. The plane is not flying in a horizontal path this time, however. So the plane is flying at an angle of 30 degrees. So the plane is actually on a rising path here. So the plane is going to be traveling along this path. But if we know this angle is 30 degrees and we know this is a right angle, then we know this angle is 120 degrees. All right, our question says, at what rate is the distance from the plane to the radar station increasing? So our plane at some point, we're going to be interested in a minute later. So over here is our plane. So we are interested in how fast is this distance between the radar station and the plane changing. So we've got three sides to the triangle. I don't see them on an XYZ axis, but you could call them XYZ, or I could call them sides A, B, and C. The interesting thing here is that we know one of the sides is 1 kilometer. B, the distance for the plane is changing, and C, this distance between the plane and the radar station is changing. So those have to remain as variables. All right, let's again make it clear what's given. We are given the rate of the plane. So that would be how distance B is changing in my diagram. You might use a different variable, but the distance B for the plane is given to be 300 kilometers per hour. And because I notice that we're interested in using a minute of time, you might want to say or. So you might also want to do the equivalent here. If it's 300 kilometers per hour, then divide by 60, it would be 5 kilometers per minute. So you'll be able to choose whichever of those two rates is appropriate. And we don't want to prove, we're not in geometry, we want to find the rate of change in the distance between the plane and the radar station. So that's my variable C. So you might have picked a different letter, but whatever variables you choose here. So we're looking for dc dt. So we need an equation that revolves around B and C, or gives us a relationship between B and C. Well, if this were a right triangle, we would want to use Pythagorean theorem. But it's an oblique triangle. Remember, any triangle that's not a right triangle can be called an oblique triangle. And notice that we're given this angle 120. So we could set up as our static formula here. So not from geometry, but from your trigonometry, we know the law of cosines, or at least I hope you could look it up if you've forgotten the law of cosines. So c squared is almost like Pythagorean theorem, but then we add this minus 2 times AB, and then cosine of the angle between them. So the angle between them is the angle across from side C. So this is the law of cosines for our side angle side case. All right, so some of the things that we can simplify for this problem, which make it a lot easier. We know that A is never changing. Side A is always 1 kilometer. And so we can put that in both cases here. So A becomes 1. And we know our angle is 120 degrees. And even easier than that, think about the cosine of 120. Let me draw that up here. Here's 120 degrees. The cosine of 120 degrees is negative 1/2. So the negative 1/2 will cancel with this 2, and then we can make that sign positive. So we've got our formula simplified. So we'll have a 1 plus b squared. Well, I suppose I should change the order of those terms. How about making it b squared first? And then this term is a b, and then plus a 1. So it kind of looks like a quadratic. So there's our static formula. It came from law of cosines. All right, so now we can do our related rates by differentiating with respect to time. So I think this part, I hope, is going quickly for you now. 2c dc dt equals 2b db dt plus the derivative of b is 1 db dt, and the derivative of the 1 is, of course, 0. So there's our related rates model, and remember that db dt was given. So this time we can't divide by 2 because this third term, this db dt, is not divisible by 2. So now we've got our formula, and in a minute we can plug in our specific case. But we have to take a detour in that specific case because notice we're going to want to plug in a value for c, and we don't have the value of c. So let's go back and make another diagram and let's see what our specific case is. So this is 1 minute later. After the plane was above the radar station, it's going to be flying for 1 minute. So I think you can see that if the plane was flying for 1 minute at 300 kilometers per hour, or 5 kilometers per minute, that 1 minute later it would have traveled 5 kilometers. And this vertical height is still 1 kilometer, and this angle is still 120 degrees. So we need to find this side, which was my variable c, and we know exactly how to do that. We've got our related rates formula. We've got our related rates formula already simplified. So we can simply say that c squared is b squared, that's the 5, plus b plus 1. So our c squared should be 31. So c, since it's a distance, we'll keep positive square root of 31. So this is our specific case 1 minute later. So after 1 minute, the plane has traveled. After 1 minute, the plane has traveled 5 kilometers. And then I used our law of cosines relationship to find the value of c. Okay, so now we're going to take these values and we're going to substitute into our related rates. So I'm going to keep the 2. Our value of c we just discovered, square root of 31. dc dt is what we're looking for, so that stays as our variable. On the other side, our value of b is our 5 kilometers, and our db dt, now we're using minutes, so if we want to answer in minutes, we should stick with the rate of 5 kilometers per minute. So our b is 5 kilometers, and our dB dt is kilometers per hour. So those 5s have different units on them. And dB dt comes here also at 5. All right, so if we do some cleaning up here, so over on the right-hand side, we have 55. And if we divide, so 55 over 2 square root of 31, and this is in kilometers per minute. If you had put in the speed of the plane per hour, if you had changed, if you had put in for these two speeds the 300, then you would have come up with dc dt. So if you had used the 300 kilometers per hour, then our answer would be exactly the same as this answer multiplied by 60. So it really is up to you whether you use that rate in miles or kilometers per minute or kilometers per hour. And I think let's see what this would be if it's reasonable. I'm going to grab a calculator and approximate. I have approximately 296.349 kilometers per hour. So that would be reasonable for the speed of a plane. Would be moving pretty fast to be that low, although I think so. It might not be too reasonable. All right, let's move on. A couple of these are repeat problems and a couple are new problems. So here we've got a camera and we are following the launching of a rocket. So the angle of elevation of the camera has to change in order to keep the rocket in sight. All right, so if we assume that the rocket is rising vertically, so here's the rocket is going to be going up this direction, and our camera is over here. So the rocket is moving up and our camera is going to follow the rocket. So as the rocket rises, so does the camera. So our angle theta is going to be changing here. And we are told that the speed of the rocket is 600 feet per second. So if we use h for the height of the rocket, we are given the dh dt. The dh dt is the speed the rocket is rising. All right, and the camera is positioned 4,000 feet from the launch pad, so this is going to be a fixed distance, not a variable. So we've got two things that we have to find. In part A, we are asked to find how fast the distance is changing from the camera to the rocket. So if I used a C for hypotenuse or a Z, it just doesn't matter, a distance D, whatever variable you want to use here. This one does happen to be a right triangle, so instead of H, you could have called this a dy dt for a height, and then you could have said that X was given to be 4,000, so it's really up to you which way you want to do this problem. If we set this as looking for dz dt in part A, then we could find a formula that involves the sides of the triangle. So then I think for part A, our static formula will be our Pythagorean theorem. 4,000 squared is one side of the triangle, and our y-coordinate is the vertical side of the triangle, and it is changing as the rocket rises, and z is the hypotenuse, which is changing the distance between the rocket and the camera. So when we do our differentiation, the derivative of 4,000 squared will be 0. 2y dy dt equals 2z dz dt. So we can divide everything by 2 here. And our specific case is when the rocket has risen 3,000 feet. So our specific case for both of these, part A and part B, we're going to have the rocket at a height of 3,000. So I think you can see that we're saved some work here, 3, 4, 5 triangle. So we know our z value is going to be 5,000 at this point. So our y value is 3,000. Our dy dt was the rate the rocket was rising. That was the given. And on the other side, our z value is 5,000. And the variable we're looking for is dz dt. So we can divide both sides here. And I think we're going to come up with 360 if I'm reading my notes correctly. And our units are in feet and seconds. And now for part B of this problem, let's think what's given and what we're looking for in part B. We're still given the speed of the rocket, of course, but now in part B, we're looking for how is the angle of elevation changing. So that's our angle theta. We've got to keep tipping the camera higher and higher to follow the rocket. So in part B, we're looking to find d theta dt. How is the angle changing? So now we're given, remember, same as in part A, we're given dy dt. So we want to have a formula that relates the vertical side y with the angle theta. And notice that we are given the adjacent side here. So we're opposite side y and adjacent side, so we could use tangent. We also know the hypotenuse, so we could do a different formula, but I think the easiest formula for part B might be to say that the tangent of theta is the opposite leg, which is going to keep changing. That's going to be our y, divided by the adjacent side, 4,000. So remember not to put 3,000 in there yet for y. Y is always changing, so you can't put in the specific case until you do the derivative. So make sure you have this as a variable. So our derivative then would be secant squared theta d theta dt. And this is 1/4000th as a coefficient of y, 1/4000th of y, so the 1/4000th can come in front, and the derivative of y is our dy dt. And now we can plug in our specific case because we can tell the secant. Remember that secant is 1 over cosine. So we know that the definition then of secant would be the hypotenuse over the adjacent leg. So if we read, remember our specific case, up here was our 3, 4, 5. Let me draw that a little bit better. Our 3,000, 4,000, 5,000. Maybe we want to see it again. Here's our theta. So our opposite side for our specific case is 3,000 feet, and our adjacent side is 4,000 feet, but the hypotenuse was 5,000 feet. So for secant, we want to choose the hypotenuse over the adjacent. And of course we can divide by 1,000 and just make that 5 over 4. And then we're going to square it. So this is our secant squared, 5 over 4 squared. D theta dt is our variable that we're looking for. And on the other side, the dy dt is the 600 kilometers per hour. So we can do some canceling over here as well. So we can at least divide by 200. So this would give us a 20. And on this side, we'll have 25 over 16. So if we want to solve for d theta dt, we'll multiply both sides by the reciprocal. So we'll have 3 over 20 times 16 over 25. And we can simplify and come up with 12 over 125. And this would be in radians per second. This is how fast, remember, we're tipping the camera. So our units here would be in radians per second. Questions 4 and 5 are similar to ones we've done before, so I'm not going to take the time to do those in the video, but let's go to number 6 because it's a bit new as well. So it's practice, similar. We've got a hot air balloon that's rising vertically. An observer on the ground is 2,000 feet, so the balloon here is rising. and we're a distance of 2,000. And we don't have a unit there. I suspect it is. So here we've got meters. So I think meters should have been given there in the problem as well. So here's the observer. And we know the observer's line of sight increases at a rate of, so this time we're actually given the d theta dt. So remember that as the balloon rises, your sight line is going to keep increasing. So we don't know the value of theta. The value of theta keeps changing, but the rate at which it's changing is given to be 1/2000th. So this time we're given d theta dt as 1/2000th radians per second. All right, and our question says, how fast is the balloon rising? So we can either call this a y coordinate or a h for a height. So we are looking for either a dy dt or a dh dt, your choice of variables here. All right, so again, look at what we need is an equation that relates theta with the vertical height. And we know the adjacent leg, so opposite leg and adjacent leg. So I think our static formula here, again, the one I would choose would be tangent of theta is h over 2,000. If you found that confusing, we could say that h over 2,000 is the same as 1/2000th times h. So either way, same thing, the opposite leg over the adjacent leg. So then our related rates model comes from differentiating with respect to time. And the derivative of tangent, we've seen this a minute ago, is secant squared with a chain rule d theta dt. And on the right-hand side, the derivative is the coefficient, 1/2000th, and then our dh dt. So now we need our specific case. So our specific case is when the balloon reaches 3,000 meters. So our specific case, if we make another diagram here, this horizontal side is fixed at 2,000 meters. And now our vertical height is 3,000 meters. So we could do Pythagorean theorem. This is 1,000 times 2, 1,000. All right, I think 1,000 times 3. So our hypotenuse would be 1,000 times 2 squared plus 3 squared. 2 squared plus 3 squared, 4 and 9 is square root of 13 for our hypotenuse. And we need the hypotenuse in order to do the secant. So remember that our definition of secant, if cosine is adjacent leg over hypotenuse, then secant is hypotenuse over adjacent. So that's why we needed this side. So we want our hypotenuse, 1,000 square root of 13 over adjacent 2,000. And we could simplify that. So let's cross out the zeros. That's our secant, so we need to square it. And our d theta dt was given this time to be 1 over 2,000. And on the other side, we're looking for dh dt. So let's see what happens here when we square this term. The square root of 13 squared becomes 13. The square of 2 in the denominator is 4. And can you see that we're going to multiply this side by 2,000? That, in other words, aren't these two terms going to cancel each other out? So I think that dh dt is 13 over 4. And our units here were in meters and seconds. And I know this video's a little long, but let's quickly at least set up question 7. This time we've got a plane flying horizontally. The altitude is 1 mile above the ground and it passes over a radar station. So like the one we did earlier, but this time the plane is flying on this horizontal. So this time the plane is, so we don't have to use law of cosine. This time the distance between the plane and the radar station will be a right triangle. So again, depending on what variables you want to use, A, B, C, X, Y, and Z, your choice. We know that the Y height here is fixed at 1 mile. All right, and we know the speed the plane is flying at. This plane is flying horizontally, so we are given the dx dt. The rate the plane is flying horizontally, 500 miles per hour. And we are looking for the rate at which the distance from the plane to the station is changing. So we want to find our dz dt. So our relationship that contains x and z is our Pythagorean theorem. So our static model is just Pythagorean theorem, but notice that our y-coordinate is always 1. The y-coordinate here is fixed. So this related rates goes a little faster. Related rates model. Differentiate with respect to time. The derivative of the 1 will be a 0. And this should say dz dt. Well, and we could divide the 2's. So we've got our related rates model. All right, our specific case. Our specific case is when the plane is 2 miles from the station. So our specific case, maybe give myself some room there. Our specific case triangle, the vertical height is always 1 kilometer, and the distance between the plane and the radar station is 2 miles. Oops, kilometers and miles. I guess this is 1 mile. All right, so we could do Pythagorean theorem. 1 squared plus x squared is equal to 2 squared, so shouldn't x be the square root of 3 if I do Pythagorean theorem? Check it out again. If I square 1 squared plus square root of 3 squared is equal to 2 squared. So I think I did that right. So our x coordinate for our specific case is the square root of 3. Our dx dt was the speed of the plane. Our z is 2 miles, and dz dt is what we're trying to solve for. So our dz dt, if we divide both sides by 2, is 250 square root of 3 miles per hour. And we could round that off as a decimal if you wish, but an exact answer is always fine.